In 1964, a plane took off from a secret airbase in the Nevada desert that would break every rule of aviation. It could fly at 3 times the speed of sound. It could reach altitudes where the sky turned black and the curvature of the earth became visible. And for over 2 decades of operational service, not a single enemy missile ever touched it. Not one. When surface-to-air batteries locked onto this aircraft, the pilot's response was simple: accelerate. The faster the missiles came, the faster the plane flew. By the time hostile radar operators realized what they were tracking, it was already gone, leaving only a sonic boom and the echo of failure in its wake. This was the Lockheed SAR-71 Blackbird, and the man who designed it did so with a slide rule, a pencil, and a philosophy that would change aviation forever. Clarence Leonard Johnson was not born into privilege or prestige. He arrived in Ishpeming, Michigan in 1910, the 7th of 9 children in a Swedish immigrant family. His father worked in the iron mines, money was tight, education was uncertain. But young Kelly, a nickname from a childhood fight, possessed something no amount of poverty could suppress: an obsessive fascination with how things flew. At age 12, he built model aircraft in his family's basement. Not simple toys. They were detailed, carefully engineered miniatures that actually flew. He tested them in the frozen Michigan winters, watching how wind affected their flight, adjusting control surfaces, and learning through iteration what textbooks had not yet taught him. His teachers noticed, but more importantly, Kelly noticed something about himself. He could see aircraft as complete systems in his mind. He could visualize airflow over wings. He could predict structural loads and aerodynamic behaviors before the math confirmed them. This was not normal. This was something else. The University of Michigan accepted him in 1928. He studied aeronautical engineering at a time when the field was barely 30 years old, when aviation itself was still considered somewhat miraculous, when most people had never flown and many never would. His thesis project became legend among the faculty. The Lockheed Electra, a new commercial aircraft, was experiencing severe tail vibration problems. Lockheed's own engineers were baffled. Kelly Johnson, still a student, analyzed the design and identified the issue. The twin vertical stabilizers were positioned in the propeller wash turbulence. His solution was precise, mathematical, and correct. Lockheed hired him immediately upon graduation in 1933, bringing him to Burbank, California for $83 a month. He was 23 years old. He would work for Lockheed for the next 42 years and never work anywhere else. But 1933 was the depths of the Great Depression. Aviation companies were struggling. Lockheed was perpetually on the edge of bankruptcy, surviving on military contracts and the occasional commercial order. Johnson worked on everything: structural analysis, wind tunnel testing, design modifications, and performance calculations. He learned the entire process of aircraft development from propeller to tail. He learned something crucial about bureaucracy. It slowed everything down. Committees debated, departments feuded, paperwork multiplied. Meanwhile, the aircraft sat unfinished. Johnson began to develop a philosophy: small teams, minimal oversight, direct communication, trust the engineers, build it, test it, fix it, repeat. No bureaucratic interference, no endless meetings, just talented people solving problems. He did not know it yet, but this philosophy would soon be tested under the most extreme pressure imaginable. December 1941, Pearl Harbor burned. America entered World War II utterly unprepared for modern air combat. The military needed new aircraft immediately. Not in 2 years, not in 18 months. Now. In early 1943, the Army Air Forces approached Lockheed's with a problem that seemed impossible. The British had intelligence about German jet aircraft development. The Messerschmitt Me 262 was reportedly approaching operational status. It was fast. It was deadly. And America had no jet fighter to counter it. None. The military wanted Lockheed to design and build America's first jet fighter. The timeline they proposed was 180 days. Lockheed's executives laughed nervously and suggested that was wildly optimistic. Kelly Johnson didn't laugh. He studied the specifications, ran some preliminary calculations, and made a counteroffer. 150 days, 5 months. He would deliver a flying prototype in 150 days, or he would resign. The executives stared at him. Building a conventional aircraft took years. Building a jet aircraft, a technology America had barely experimented with, in 5 months was insane, impossible. Kelly repeated his offer, 150 days, but he had conditions. He needed complete autonomy, no interference from company management, no military oversight beyond essential liaison. He would handpick his team, maybe 24 engineers. They would work in total secrecy in their own facility, away from the main plant. They would have direct access to the machine shop. They would make decisions immediately without committee approval. They would work every day, around the clock if necessary, until the aircraft flew. The executives calculated the risk. Kelly Johnson had never failed them. His track record was flawless. They agreed. On June 23, 1943, Johnson received official authorization. He rented a circus tent next to a foul-smelling plastics factory, erected it next to the Lockheed wind tunnel, and assembled his team. Someone joked it was like working next to a skunk works. The bootleg distilleries hidden in the Appalachian woods. The name stuck. The Skunk Works was born. 143 days later, on November 16, 1943, the XP-80 Shooting Star rolled out for its first flight. It was not 150 days, it was 7 days early. The aircraft worked perfectly. It flew at 502 miles per hour, faster than any American fighter in service. It climbed like nothing the test pilots had ever experienced. It handled beautifully. The military was stunned. Kelly Johnson had delivered exactly what he promised, ahead of schedule, and it exceeded every specification. The Skunk Works methodology was vindicated. But this was only the beginning. The real test was coming. The Cold War was approaching. And the demands it would place on Kelly Johnson would make the XP-80 look simple. By the mid-1950s, the Soviet Union was closed, tighter than a vault. America's intelligence agencies needed to know what was happening behind the Iron Curtain. Satellite technology did not exist yet. Spy networks were unreliable. The CIA needed eyes in the sky that could fly over Soviet territory, photograph military installations, and return with the intelligence before Soviet fighters could intercept. The problem was physics. Soviet air defenses were formidable. The new 75 Dvina surface-to-air missile system could reach altitudes of 65,000 feet. Soviet MiG fighters could intercept anything flying lower. The CIA needed an aircraft that could fly higher than any missile could reach and faster than any fighter could catch. They needed to do it without being detected. And they needed it soon because the Soviet nuclear program was accelerating and American intelligence was flying blind. Kelly Johnson studied the requirements and saw immediately that no existing aircraft could meet them. This needed to be something entirely new, not a modified bomber, not an upgraded fighter, but something purpose-built for one mission: fly higher and faster than anything else in the sky. He began sketching designs in early 1954. The aircraft that emerged from his pencil looked like nothing else flying. It had long, slender wings for high-altitude efficiency. It had a lightweight airframe built from aluminum and titanium. It had a single turbojet engine mounted high in the fuselage, and it had one radical feature that would define its appearance. To reduce radar cross-section, Johnson designed it with the smallest possible frontal area, giving it a sleek, almost fragile appearance. He called it the U-2. The CIA loved it. They ordered it immediately. Johnson promised delivery in 8 months. He delivered in 7. The U-2 began flying reconnaissance missions over the Soviet Union in 1956, operating at 70,000 feet, above the reach of Soviet interceptors. It was extraordinary. It was unprecedented. And Kelly Johnson knew it would not last. Soviet technology was improving rapidly. By 1960, a new surface-to-air missile system achieved the previously impossible. On May 1st, a Soviet S-75 missile shot down a U-2 over Sverdlovsk, forcing pilot Francis Gary Powers to eject and creating an international incident that shattered a planned peace summit. The U-2's invulnerability was over. The CIA needed something else, something that could not be shot down even if detected. The requirements this time were staggering. The new aircraft needed to fly at a minimum of 85,000 feet. It needed to cruise at Mach 3.2, over 2,100 miles per hour. It needed to do this for hours. It needed to carry reconnaissance equipment and enough fuel for missions covering thousands of miles. And because it would be flying at speeds and altitudes no aircraft had ever sustained, it needed to survive conditions that would destroy conventional aircraft. Every system would have to be redesigned. Every material would have to be reconsidered. Every assumption about aircraft design would have to be questioned. Kelly Johnson accepted the challenge with characteristic confidence. But this time, even he understood the magnitude of what he was attempting. In 1959, he began developing what would become the A-12, the predecessor to the SR-71. The problems appeared immediately, each one more severe than the last. At Mach 3, air friction would heat the aircraft's skin to over 600 degrees Fahrenheit. Aluminum melts at 660 degrees. The entire airframe would have to be built from titanium, a metal so difficult to work with that most aerospace companies avoided it entirely. Titanium welding required inert gas environments. Titanium machining destroyed cutting tools. Titanium thermal expansion was unpredictable. And in 1959, the United States had almost no titanium production capacity. The Soviet Union, ironically, was the world's largest titanium producer. The CIA had to set up shell corporations to purchase Soviet titanium, which was then used to build an aircraft designed to spy on the Soviet Union. The absurdity was not lost on Johnson. Material problems were just the beginning. At Mach 3, the aircraft fuel would heat to temperatures that would boil conventional jet fuel. Johnson needed a fuel that remained stable at high temperatures. The answer was JP7, a specialized kerosene-based fuel with an extremely high flash point. It was so stable that you could drop a lit match into it and the match would extinguish. But this stability created another problem. JP7 was so difficult to ignite that the engines needed a chemical starter system using triethyl borane, which ignited spontaneously on contact with air. Every engine start required injecting this pyrophoric chemical. The complexity was multiplying. Then there was the airframe itself. At 600 degrees, the titanium fuselage would expand several inches. The aircraft had to be designed to accommodate this expansion. Panels had to fit loosely on the ground, creating gaps that actually leaked fuel. Only at operational temperature would everything seal properly. This meant the aircraft would literally drip fuel while sitting on the runway before takeoff. Kelly Johnson was designing an aircraft that leaked fuel on the ground, required exotic chemical ignition systems, and was built from a metal his machinists barely knew how to work with. Any sane engineer would have quit. Johnson kept pushing. The shape of the aircraft presented its own challenges. For minimal radar reflection and maximum speed, Johnson designed an extremely sleek profile, but this created aerodynamic instability. The aircraft wanted to pitch and yaw at high speeds. Conventional control surfaces could not respond fast enough. Johnson pioneered the use of rudder-assisted turns, where the inward-tilted vertical stabilizers created a coupling between yaw and roll. Banking the aircraft required coordinated rudder input. Pilots would have to relearn basic flight mechanics. The cockpit environment was equally extreme. At 85,000 feet, the air pressure was so low that the pilot blood would boil without pressurization. The pilots wore full pressure suits, essentially spacesuits, while flying. If cabin pressure failed, they had minutes to descend before losing consciousness. The temperatures were brutal. While the skin reached 600 degrees, the cockpit windows reached 350 degrees. The glass had to be specially formulated quartz. Even the tires were unprecedented. They were filled with nitrogen instead of air to prevent explosion from heat. They were made from aluminum-impregnated rubber. Each tire could be used only once because landing heated them to their structural limits. By 1962, the A-12 was flying. It worked, mostly. But it was a CIA aircraft, classified beyond top secret, and limited to reconnaissance missions. The Air Force wanted its own version with additional capabilities, a two-seat configuration for a reconnaissance systems officer, side-looking radar, and enhanced countermeasures. Johnson took the A-12 design and modified it, creating what would be designated the SR-71. The changes were subtle but significant: slightly larger fuel capacity, a modified nose section for additional sensors, enhanced electronic countermeasures. The final aircraft was 107 feet long, with a wingspan of 55 feet and a height of 18 feet. Empty weight was 67,500 pounds. Maximum takeoff weight was 172,000 pounds. Power came from two Pratt & Whitney J58 turbojet engines, each producing 32,500 pounds of thrust with afterburner. These engines were themselves revolutionary. At Mach 3, traditional turbojet efficiency collapsed. The J58 used a unique bypass system where inlet shock cones adjusted position to manage airflow, and at high Mach numbers, 80% of the thrust came from the inlet and bypass system rather than the engine itself. The engine essentially became a ramjet at cruise speed, nothing like it had ever been built. On December 22, 1964, the first SR-71 flew from Air Force Plant 42 in Palmdale, California. It was painted dark blue, almost black, to dissipate heat and reduce visibility. The media nicknamed it the Blackbird, though officially the name was never used by Lockheed or the Air Force. The name stuck because it was perfect. This aircraft looked sinister. It looked fast sitting still. It looked like it came from the future, and when it flew, it rewrote every assumption about what aircraft could do. Operational missions began in 1966. The Blackbird was based at Beale Air Force Base in California and deployed to forward bases as needed. Missions over Vietnam, North Korea, the Middle East. Every time hostile radar detected it, the response was the same. Missile batteries would light up, launch warnings would sound, missiles would climb toward the Blackbird, and the pilot would push the throttles forward. The Blackbird would accelerate. Mach 3.0, Mach 3.1, Mach 3.2. The missiles, maxing out at Mach 3.5 in ideal conditions and losing speed as they climbed, could not catch it. They would exhaust their fuel and tumble back to Earth. Over 4,000 missiles were fired at SR-71 aircraft during operational missions. Not one ever connected. Not one. The missions themselves were grueling. Pre-flight preparation took hours. Pilots suited up in pressure suits, undergoing physical examinations to ensure they could withstand the stress. Engine start required precise timing with the triethylborane injection. Taxi to the runway left a trail of JP-7 fuel dripping from the loose panels. Takeoff required careful monitoring because the aircraft was unstable at low speeds. Climb to altitude took time and precise navigation because the turning radius at cruise speed was over 100 miles. Once at operational altitude and speed, the pilots existed in a unique environment. Outside the windows, the sky was black, despite being daytime. The Earth's curvature was visible. The stars were visible. They were at the edge of space, flying faster than a rifle bullet, covering 36 miles per minute. A flight from Los Angeles to Washington, D.C. took 64 minutes. The missions could last hours, requiring multiple aerial refuelings because the fuel consumption was massive. Then came the descent, the landing, the post-flight inspection where ground crews would inspect every inch of the titanium skin for stress cracks and heat damage. The records speak for themselves. On July 28, 1976, an SR-71 set the absolute speed record for a manned air-breathing jet aircraft, 2,193 miles per hour, Mach 3.3. On the same day, it set the altitude record, 85,069 feet. These records still stand. No aircraft has broken them. On September 1, 1974, an SR-71 flew from New York to London in 1 hour and 55 minutes, averaging over 1,800 miles per hour. The return flight from London to Los Angeles took 3 hours and 47 minutes. The Blackbird crossed the United States coast to coast in 68 minutes. It flew around the edge of space for 24 years, collecting intelligence that shaped American Cold War strategy, and never lost a single aircraft to enemy action. Mechanical failures occurred, accidents happened, but no enemy ever touched it. Kelly Johnson retired from Lockheed in 1975, though he remained as a consultant until his death in 1990. His legacy at the Skunk Works included the U-2, the SR-71, the F-104 Starfighter, and numerous classified projects that transformed military aviation. His management philosophy became legendary. The Skunk Works operated with 14 basic principles: strong but small project offices, limited reporting requirements, minimal paperwork, swift decisions, protection from bureaucracy, access to manufacturing, minimal inspections, incentives for performance, mutual trust, elimination of non-essential functions, and absolute security. These principles seemed simple. They were revolutionary. They allowed small teams to accomplish what large bureaucracies could not. They proved that innovation thrived when engineers were trusted, empowered, and freed from administrative burden. The SR-71 was the ultimate validation of this philosophy. A small team, working in secrecy with minimal oversight, created an aircraft that remained unmatched for decades. The SR-71 was officially retired in 1998, though a few were briefly reactivated in the mid-1990s. The stated reason was cost. Each flight hour required extensive maintenance. The specialized fuel was expensive. The strategic reconnaissance role could be filled by satellites. But the truth was simpler. Nothing could replace the Blackbird because nothing needed to. Satellites had taken over the reconnaissance mission. Unmanned aerial vehicles were emerging for tactical intelligence. The Blackbird had no peer and no successor because the mission it was designed for had evolved beyond manned aircraft. When the last SR-71 made its final flight, landing at the Smithsonian's museum facility, it set one last speed record on the journey. The era of the Blackbird was over, but its legend was just beginning. Today, SR-71s sit in museums across America, at the Smithsonian National Air and Space Museum, at the Museum of Flight in Seattle, at the Strategic Air Command Museum in Nebraska, at Beale Air Force Base, at NASA Dryden. Visitors stand beneath these massive aircraft and struggle to comprehend what they are seeing. The sleek black titanium skin, the massive engines, the cockpit windows barely large enough for the pilot's helmet. These aircraft look fast, they look dangerous, they look like they could still outrun anything in the sky. And in many ways, they could. No operational aircraft today can match the SR-71's sustained speed and altitude combination. The technology exists to build something faster. The materials are available. The computational tools are vastly superior to Kelly Johnson's slide rule, but the will and the mission do not exist. The Blackbird represented a unique moment in history when human ingenuity, Cold War urgency, and engineering brilliance converged to create something that transcended its original purpose and became a symbol of what is possible when talent is unleashed and bureaucracy steps aside. Kelly Johnson died on December 21, 1990, at the age of 80. His obituaries celebrated his achievements. Fellow engineers mourned his passing, but his true memorial flies in museums and lives in the minds of everyone who has ever seen an SR-71 Blackbird and wondered how it was possible. The answer is visible in every rivet, every panel, every system. It was possible because one man refused to accept limitations, because he trusted small teams over large committees, because he valued results over process, because he understood that innovation requires freedom, speed requires focus, and breakthrough requires the courage to attempt what others call impossible. The Blackbird did not just outrun missiles, it outran conventional thinking. It proved that the right team, with the right leadership, with the right philosophy, could accomplish in months what bureaucracies could not accomplish in years. That lesson remains relevant. That legacy endures. And somewhere, in a museum, under lights, behind ropes, sits a black titanium aircraft that once flew at the edge of space, faster than anything else with a human pilot, designed by a man with a slide rule who simply refused to believe that impossible meant anything more than not yet done.